Hello, everyone. I'm Tong. Today it's my pleasure to share our experiences in managing the performance and the reliability of a large-scale genomics cloud platform. This is a joint work with Professor Robert Grossman, Professor Haryadi Gunawi at the University of Chicago, and most of the work was conducted in the Center for Translational Data Science. Bioinformatic pipelines or workflows are often non-running and can take days or weeks to complete. Bioinformatics is an interdisciplinary subject that develops and uses algorithms, methods, software, and systems to help humans explore and understand biological data. We share our technical experiences in investigating the performance of long-running bioinformatics pipelines on the Genomic Data Commons. The Genomic Data Commons processes cancer data, which is several million core hours of data processing per week, per month, and makes available the data to the public. And now there are 3.7 petabytes of data available today. First, let me give some background information on the platform and our systems. The core of the platform is the pipeline execution engine and the execution environment. Pipeline execution engine consists of the specifications for the pipeline language, such as CWL, WDL, Nextflow, and the execution model for the engine. Some pipelines are run in simple parallelization or embarrassingly parallel, while some other pipelines are developed in MapReduce or Spark framework. The execution environment is a HPC cluster or distributed cluster, and some platforms may also use a cloud system to run pipelines. GDC, which is short for Genomic Data Commons, co-locates data, storage, and computing infrastructure, and is designed to store and analyze cancer genomic data and associate clinical and image data from NCN and other projects. Data for a single sample is 10 to over 100 gigabytes in size, and the total data volume stored is 7.2 petabytes, including both public and internal data. GPass, which is short for GDC Pipeline Automation System, is the analysis platform supporting the GDC. It is built on a large-scale on-premise cluster that consists of bare metal nodes and OpenStack KVM managed VMs. It uses CWL tools as the pipeline execution engine. Now in this section, I will briefly introduce how the workloads in GPass look like. As shown in the graph, a bioinformatics pipeline consists of multiple tasks in which the outputs of one task are often the inputs of another task. And the task can also be another predefined subpipeline. Together, they make up with a directed graph representation. We use a large variety of bioinformatics tools, such as SAMP tools, BWA, and so on, in the tasks. The tools are written in various languages, showing different performance characteristics in terms of I/O and computation. Now we define how to measure the job performance. To distinguish one job from another, simply speaking, we need to look at the input data and the pipeline design. To be more specific, pipelines are defined by the tools and the data flow. And for the input data, in addition to the actual data content, project, which indicates the data source, and the experimental strategy, which indicates the biological organization of the data, largely define how data will be processed in a pipeline job. As a result, job performance is only comparable in the same pipeline, experimental strategy, and project. We measure the performance using job execution time divided by the input size, which we call it processing rate. Interested audience can refer to our paper for more information regarding to the tool details and the performance distributions. Now in this section, I will discuss the issue of tail performance that we found in our VMs. Here we look at the CDF of performance for a pipeline, which is called variant filtration Kindle pipeline. The green line stands for the jobs running on bare metal nodes, which has more stable performance, and the line is nearly vertical. However, the red dashed line shows that the jobs running on VMs perform worse and show the long tail. Here we'll demonstrate a simple test using a Java application, var_scan2, which is commonly used in our variant calling pipelines. The graph plots a series of experiments with var_scan2 tasks. A VM with SSD storage restarts at the start, and each task runs with 8 CPUs. In each experiment, there are 5 tasks in parallel, and the VM idles for 30 seconds in between the experiments. We can see that prior to point B, the execution time for each experiment is short and stable. However, beyond point B, the experiments are getting slower and slower. We refer to the VM prior to B as fresh VM, and the VM beyond point B as an aging VM. When the VM is in the aging stage, we use the file benchmark in sysbench and monitor the CPU utilization. And the CPU utilization is calculated from the start file stored in a system file as shown in the graph. It records the CPU slices in the unit of 10 milliseconds since the system boots up for each CPU in all categories, such as user, needs, system, and idle, and so on. Here we use user and system to demonstrate calculations. We define utilization rule as the sum of user and system divided by time t seconds. And we also defined utilization derived as the sum of user and system divided by all the slices, which is also the same way that utilization is calculated in the top command. Usually these two are equivalent because in value, all slices are equal to slices per second times t seconds. And slices per second are usually hard-coded into the kernel as 100. Now we only present the benchmarking results for VIO here because other benchmarking results does not show much difference between aging VM and fresh VM. And we can see that in the graph showing CPU utilization for the aging VM and its host, there's a gap between utilization raw and utilization derived on the VM. It essentially means that next slices are recorded in the VM. Besides, we can notice that the system usage in the dashed green line is high on the host and almost equal to the overall CPU utilization, even though the VIO is an IO-bounded workload. When it comes to the VM, there's only 27% system usage, which means the VM have feather in the host works intensively. At last, it is worth to note that the VM is the only tenant on the host. Through the benchmarking, we found that read operation is most affected in the aging VM. So we modified the kernel a little bit to record the time spent in each step of read operation. Roughly, a read operation goes through 5 steps. Step 1 is it checks the page cache. Step 2, it performs synchronized read. Step 3, it sends out asynchronous read and does not wait. Step 4, it waits for any necessary asynchronous read to complete. Step 5, it copies data from kernel space to user space. IO latencies are usually reflected at step 2 and step 4. It turns out that most of the time is spent in step 5, copy page. And the graph to the right shows that copy page does not only take up most of the time, but also increase significantly with the increase of processes. We also need to note that the copy page operation is a pure memory operation. After a long investigation, we found that if the extremely high system CPU usage and memory slowdown are mainly caused by the extended page table. Extended page table, or EPT, is an implementation of second-level address translation to maintain memory address translations from guest OS to host OS. A miss in EPT, similar to a page fault, is called an EPT violation, and it will result in a VM exit, which is a very expensive event. In another experiment, where we run 5 real DNA alignment pipeline jobs, and each job uses 6 CPUs, and we run them repeatedly on a fresh VM for more than 10 days. We collect the number of VM access that handles EPT violations observed every other 5 minutes. And then after more than 10 days, we plot the average EPT violations over 5 minutes period and throughout each job execution and the job execution time. We found that the longer VM has been running, the more EPT violations there will be, and the longer execution time it will take. We defined a new metric as the address distance of subsequent EPT violations, and it essentially represents the level of memory fragmentation. This graph shows the distance distribution for the experiment, and the larger distance means subsequent EPT violation addresses are farther apart. So the memory tends to be more fragmented and more EPT violations occur. Now we share a few methods to detect and mitigate the performance slowdown. Having known that the slowdown is caused by EPT violation, we developed 2 methods to monitor the slowdown. The first method is host-level EPT violation monitoring that we also used in the experiment in the previous slide. We use the metric we defined in the experiment and rely on the distribution of the distance. This method requires tracing on the host, and we do not observe performance impact based on our earlier experiment. And we can see that there's an obvious difference at day 3. Thus, it is a good indicator to warn that VM begins to slow down. The other method utilizes the CPU slice difference between host and VM. Here we define vCPU efficiency as slices recorded in the VM divided by the slices recorded in the host. The efficiency less than 100% means that the VM loses some slices from the host due to intensive hyperfeather activities. This method is simple and low overhead, but it can only detect the slowdown when the slowdown occurs. And the result can be offset when many CPUs are idle. As in the table, heavy workloads uses 40 CPUs, and the light workloads uses 8 CPUs. And we run them on fresh VM and agent VM. And we can see that the difference for heavy workloads is obvious, but for the light VM, execution time increased a little bit on the agent VM, but the efficiency remains high. For mitigation, we demonstrate 2 methods that we tried here, and please refer to the paper for the other 3 methods. The first method is defragmenting memory. We can use the built-in tool to achieve this, and it can increase performance and decrease EPT violations. However, it's simply impossible to get the VM back to the fresh state. As shown in the table, defragmenting on the 7th day can increase performance and decrease EPT violations. However, it is still much worse than the fresh state. Finally, we also evaluated 2 public cloud solutions. AWS and Google Cloud both have specialized hyperfeathers, and they do not disclose the optimizations in their VMs. The tests we conducted are the DNA alignment jobs, and the jobs start to slow down from the 4th day on our on-prem VM. As the table shows, with AWS and Google Cloud, we have done a lot of more tests, and they show far more consistent performance for the jobs. In conclusion, from what we have tested, public clouds can provide reliable performance, but the costs are generally higher. Moreover, there are some limitations in our tests since we are using dedicated hosts. To the best of our knowledge, we are the first to conduct a prolonged performance evaluation of virtualization stack for jobs that are both long-running and memory-intensive. We hope that the contributions of this paper can help other deployments similar to ours and lead to new research activities. The GPath runs many different heterogeneous non-running workloads, developing hybrid scheduling algorithms that use both on-premise clouds and public clouds present some interesting research challenges. Thank you very much for attending my talk.